So today's video is on 7.6, dilations and similarity within the coordinate plane. If you remember from first semester, we talked about transformations. Transformations like rotations, reflections, translations. We're going to build upon that today, and we're going to introduce you to a transformation called a dilation. A dilation is a transformation that actually changes the size of a figure, but it does not change the shape. It's almost like putting a clip art into a Word document and then grabbing on one of the corners and making it a larger picture. You're not changing the shape of the figure, you're actually just changing the size. So when we're working with dilations, our pre-image, which is the figure we first started off with, and then our image, the figure that we get after our dilation, we know that those two are indeed going to be similar to each other. So they have the same shape, but they are of different sizes. So the scale factor is how much the figure is actually going to be enlarged or reduced. So we can either make it larger or we can make it smaller. And the dilation will have a scale factor of k. So either you're told what k is or you'll have to find out what k is. So if I tell you the scale factor of k and I'm asking you to tell me what the new coordinates in the image would be after a dilation, all you have to do is multiply each of the coordinates of the original or the pre-image by the scale factor of k. So if I'm going to do a dilation of a scale factor of k, I would take the x coordinate of my original point, multiply it by k to get the x coordinate of the new point, and then take the y coordinate of my old point, which was b, and multiply it by k and get the y coordinate for the new point. So for example, if I'm dealing with triangle EFG and they're giving me the vertices at E, at F, and at G, so they tell me the coordinates, what we want to do is we want to find the coordinates of the image after a dilation with a scale factor of 2. So right now, that information just told me that my k equals 2. So we're going to go ahead and we're going to start off with the original E, which was 0, 0. And we're going to transform it with a dilation. And we're going to make it E prime. That's going to be the coordinate for E in my image now. And by doing that, we were told that you take the x coordinate for the original E, and you're going to multiply it by the scale factor, which was 2. I'll take the y coordinate for my E and multiply it by the scale factor, which is 2. Now, the new E prime point will be, if I take 0 times 2, I'll get 0, and 0 times 2 gives me 0. So my new E coordinate will be 0, 0. Now you might be saying, well, that didn't change at all. Yeah, for some of them it doesn't. So we're okay. Let's take a look at F. So my original F was 1, 5. If I'm going to change it into F prime, I'll take the x coordinate, times it by my scale factor of 2, and then my y coordinate, and multiply by a scale factor of 2. So that my new f prime is 2, 10. Last one, g. G was 7, 2. If I'm going to do the transformation, my g prime, I'd take 7 times 2 and 2 times 2. So g prime will end up giving me 14, 4. So those are all the coordinates for the vertices on my image, or my triangle, E prime, F prime, G prime. In this example, we're asked to draw the border of the photo, which is given to you here, after a dilation with a scale factor of 3/2. Had to add that 3 in there. So if I know that I'm working with a rectangle here, A, B, C, D, I know that my image afterwards will be A prime, B prime, C prime, and D prime. So I have to figure out what those are. So the first thing we're going to do is we're actually going to write down what the coordinates are for my A, B, and C. A sits at the origin, so it's 0, 0. B is at the coordinate 0, 4. C sits at the coordinate 3, 4. And D sits at the coordinate 3, 0. So we're going to go ahead and find out what A prime, B prime, C prime, and D prime are. A prime, and I'm going to do this kind of quickly without writing it all down. You're going to take your x coordinate, multiply it by 3/2, which was our scale factor, and my y coordinate, multiply it by 3/2. Well, if I take 0 times 3/2, I'll get 0 in both instances. Next, B prime. B prime, if you take 0 times the 3/2, I get 0, but 4 times 3/2 ends up giving me a 6, so I will get 0, 6. C prime, when I take 3 times 3 halves, I'll get 9 halves. And if I take 4 times the 3 halves, we'll get that 6 again. D prime, the last one, 3 times 3 halves gives me 9 halves, and the 0 times our 3 halves is 0. So those are all the new points that I must put onto my graph. So let's start off with A prime. A prime is actually going to sit at 0, 0 again, so we're going to put that down there. We'll make that an A prime. B prime sits at 0, 6, so if I go all the way up to 0, 6, I'm going to put a B prime there. The next one is C prime, and C prime is 9 halves, comma 6. 9 halves is the same thing as 4.5. So I'm going to go to 4.5, and then I'm going to go all the way up to 6. So I should be somewhere right around there. Put a C prime down, and the last one was D prime, and that was 9 halves, comma 0, or 4.5, comma 0. Now that I've got those, all I have to do then is draw the border. So if I connect, hopefully with straight line segments here, there we go. You can see that you took your original photo and you made it larger. In our third example of the day, they are giving us the fact that we're dealing with 2 similar triangles. So triangle TUO, that's the smaller triangle, and triangle RSO. And we know that if they're similar, the angles are congruent and the sides are proportional. We're going to use that fact to help us find out what the coordinates for U would be and what the scale factor is from triangle TUO to triangle RSO. So first, when the triangles are given to us similar, we know that we can compare the sides and set up a proportion. So I'm going to go ahead and I'm going to compare this side, TO, to the side in the triangle similar to that, which is RO. And I know that TO over RO would be the same thing as saying that UO is compared to SO. So I'll go ahead and write that down. UO compared to SO. So let's fill in some of the measurements that we know. TO, since it's over here at -9, 0, the distance from O to T is 9 units. So we'll go ahead and put a 9 down. RO is the distance from R to O, and that would be 12 units because we were at the point -12. Taking a look at UO, we said we want to find out what the coordinates for UO, so we're going to figure out what this distance is. I'm not quite sure what it is right now, so I'm going to leave it as a UO. And the last one, SO, it's up here at 0, 16, so that means I went up 16 units. That's my distance for SO. So now all I have to do is just cross multiply and solve this one out. By cross multiplying, I will get 12 times UO is going to equal 9 times 16, which is 144. And if we divide, we get UO equals 12. So that means the distance from U to O was 12 units. So the coordinate for U is going to be 0, 12, because it's still, when I started, I didn't move left or right when I started with the point, so that would be the 0 portion, and I moved up 12 units. Now, for the scale factor, if you're talking about the scale factor, all you have to do is take a look at the coordinates. What if I take a look at the coordinates for U and S? So we have the coordinates for U. My question is, since you're working from triangle TUO to triangle RSO, what did I have to do to the coordinates for U to get to the coordinates for S? It's almost like asking you this question, okay? What did I do to take 0, 12 and turn it into the coordinate of 0, 16? Do you remember that whole scale factor thing? And we said, oh, to make this change, you would have to take your original points and multiply them by a k. So my question is, what did I do to 12? What did I multiply it by to get to a 16? So if I solve this and I divide both sides by 12, I'll get 16 twelfths. But then if I simplify that down, I'll get 4 thirds. So this tells me that my scale factor from triangle TUO to triangle RSO was 4 thirds. And if you're not quite sure about it, take the t coordinate. If you multiply -9 by 4 thirds, you end up getting a -12. So you know your scale factor is right. So for our next example, it's asking us, where it's actually giving us the coordinates for several of these points, and it's asking us to prove that triangle EHJ is indeed similar to triangle EFG. So if I need to prove this, the first step you're going to do is plot out all of the points that they gave to you. So you're going to plot out E, F, G, H, and J, and I've done that below here. Once you've plotted out your points, go ahead and connect them to make the two triangles. Now, the next step of the process is to actually use the distance formula to find the side lengths. Now, anytime you're dealing with horizontal or vertical distances, you can go ahead and just count those off. So if we're taking a look at FG, that's a nice easy one. So if I'm going from F to G, I've got 1, 2, 3, 4, 5. I know that distance is 5 units, so I'll go ahead and I'll put a 5 down for FG. And I know for HJ, if I count that off, 1, 2, 3, 4, and then I've got another 6 over here. So we know that's 10 units for HJ. Now what I need to do is I actually have to find out, and this is where you're going to come in handy, you're going to find out the distance for FE, the distance for HE, the distance for GE, and the distance for JE. And you're going to do that. While you're doing that, I'm going to do it on the side over here. You should probably actually pause the video at this point in time. That way we're not wasting video space. So pause the video, find the distances for EF, EH, EG, and EJ. We'll come back together and we'll make sure that we have the same exact distances. All right, so hopefully you ended up getting the same exact distances as I did. For EF, I ended up solving and getting the square root of 17. For EH, I ended up getting 2 square roots of 17. For EG, it was 4 square roots of 2. And for EJ, it was 8 square roots of 2. So we've got all of those distances for the sides. The next thing we want to do is we want to find the similarity ratio. Now, they were talking about proving that triangle EHJ was similar to triangle EFG. So really what I want to do with the similarity ratio when I'm comparing them is I'm going to go ahead and I'm going to pick maybe the side EH. And when I pick the side EH, I'm going to compare it to the side EF. So the length for EH we found was 2 square roots of 17. And the length for EF was the square root of 17. So if we simplify this down, I know the square root of 17 will cancel, and I end up getting a 2. So our similarity ratio from triangle EHJ to triangle EFG is indeed 2. And you can kind of take a look at that and see. If you compared EJ to EG, you would get 8 square roots of 2 divided by 4 square roots of 2. The square roots of 2's would cancel, and you're left with 2 again. So our similarity ratio is indeed 2. So how does this help us out? Well, since all of my sides then are indeed proportional, because if I compared 10 to 5, that would have a similarity ratio of 2 also. So all of the sides are proportional, and better yet, do you realize that in the smaller triangle and the larger triangle, they both share angle E? So if they both share angle E, that's reflexive, then I know that my two triangles are indeed similar by side angle side similarity, because EF was similar to EH, angle E was congruent to itself in both triangles, and EG was similar to EJ. So side angle side similarity. Okay, so in our last example, we're dealing with triangle ABC. And what we're going to do is we're going to make a dilation of a scale factor of 2/3. So what we have to then do is verify that our triangle A prime, B prime, C prime is indeed similar to our original triangle ABC. First thing you should do is, if you're given a problem like this, go ahead and make sure that you end up having some sort of graph if they give you the coordinates, or if you're lucky and they give you the graph already, you can go ahead and just skip to the next step and make sure that you multiply each and every one of your coordinates by the scale factor of 2/3. So if I want to take a look at and find out what A prime is, what we need to do is take our original x coordinate for A and multiply it by my scale factor of 2/3, my original y coordinate of 3 multiplied by a scale factor of 2/3. So A prime will turn into the coordinate of 0, 2. We're going to do the same thing for B. So B prime would be 3 times 2/3 and 6 times 2/3. So when we simplify that down, my 3 times 2/3 becomes a 2, and my 6 times 2/3 becomes a 4. For C prime, for our C prime, 6 times 2/3 and 0 times 2/3 forces our C prime to turn into a 4, 0. So now that we have our points, the next step we'll do on the next slide is go ahead and graph them. So through the magic of technology, I already have mine graphed, and what you could have done was graphed it on your original graph that you were given with the A and the B and the C on it. So now what we're looking at, we notice that, yep, okay, so my A prime, B prime, C prime, that triangle is indeed smaller. If you took a look at the scale factor, it was 2/3. So that did indeed mean that the dilation that was occurring was a reduction in the size. So what we have to do to verify that two triangles are similar is the next step. We have to go ahead and use a distance formula to find the side lengths. So we have 3 of them here. You're going to do exactly what we did before. And you know what? While you're at it, why don't you go ahead and find the similarity ratio between the two triangles also. So it's exactly what we did before with the previous example where I had you find the distance and then we talked about the similarity. So go ahead and do that for me. You can pause the video now, and when you come back, I'm going to have all of that information filled out and then we'll walk you through it. Okay, so after all of that work with finding all of the distances and finding the similarity ratios, I'm going to run you through how we found out that these two triangles are similar by side-side-side similarity. So the first thing was, I found out for my distances, I used blue to represent the original triangle that they gave us, ABC. So AB was a distance of 3 squared to 2, BC was a distance of 3 squared to 5, and AC was a distance of 3 squared to 5. For my A prime, B prime, I got 2 squared to 2, B prime, C prime, and A prime, C prime, they were both 2 squared to 5. So that was for our distances. Now, when we do the similarity ratio, since we were talking about verifying that the triangle A prime, B prime, C prime was similar to triangle ABC, I put the A prime, B prime on the top. So the primes are going on the top, and the original ones are going on the bottom. So A prime, B prime related to the AB is 2 squared to 2 over 3 squared to 2. The squared to 2's cancel, and I get 2/3. What happens then is I notice that when I do the same comparison with the other one, 2 squared to 5 over 3 squared to 5, squared to 5's cancel, and I get 2/3. And then for the last one, yep, okay, so A prime, C prime over AC ends up giving me 2/3. So I got 2/3 in all the instances, which is great. With the same scale factor for all 3 sides, that tells me that these two triangles are indeed similar by side-side-side similarity. Now, I know that was a lot, but anytime you guys have any questions regarding any of this material, make sure that you speak up and you say something. Ask your teacher. That's what we're there for, okay? So if you've got questions, make sure you ask in class tomorrow. Otherwise, have a great night.